All right, hello and welcome to Lab 3. I'm going to force you to make another hash table. I assume you made one already in CSCI 41. I'm going to make you implement a different kind with a fancier, more mathematical kind of hashing style. So let's get started. There's a lot of different pieces to this lab that involve some syntax that you may have not seen before. So first of all, an enum is short for enumeration in C++, is something that allows you to make a type. So let's go to this little documentation page. What you can do, there's also things called unions. Is that going to teach us about that? Type def. So there's unions. We're not using that. Then there are enums, which is short for enumerated things. And so read that if you're interested. But yeah, structs and classes are not the only way to make a type. You can use an enum instead. And what it is it's a way of specifying it's a way of making a type where you specify exactly what kinds of values that type can hold. Okay, so here's my motivation for an enum. Let's say that you are making a program for like Baskin Robbins or some sort of ice cream store, and like you are going to store all the flavors that your online orders are asking for as just strings. So string flavor equals vanilla, like you allow the user to type the word or something. And so you're getting a bunch of strings from the user as to what kind of flavor that they want. But let's say that you only have vanilla, strawberry, and chocolate ice cream available, and like your user asks you for like Rocky Road or sherbet or something, and like you don't have that, but like you were able to store a string with any word inside of it, right? So that's kind of unfortunate. A user could have asked you for, they could have set it to, I don't know, string flavor equals like lowercase vanilla, and that might ruin everything. Like you were only checking for uppercase or something. Like that's unfortunate. So like you have a bunch of options, and that's not really nice. Instead of using strings, you get more guarantees if you make an enum instead. All right, we get more guarantees, and this will force you to do only the right values. Guarantees with enums. And so wouldn't it be nice instead to make a type, your own little cloud called ice cream for your program, that only has as valid values just like vanilla, the word, the syntax, the symbol vanilla, then chocolate and strawberry. And you'd be forced to make your value like this. Just like you'd say ice cream as the type name, and like your flavor, ice cream flavor F, flavor 2, I don't know, is equal to vanilla without any quotes or anything. It's just a value of that type. It's a member of the type. It's an enumerated type. You're listing out all the different kinds of things it could be. And so this, like if somebody typed lowercase vanilla or Rocky Road or something, it wouldn't even compile because that isn't allowed. You've defined the ice cream enumeration, that ice cream type, to only hold those things. And so this is how you create that type in C++. You say enum ice cream, and then in between braces you put all the different values that you want of that type. So you're listing all of them out. Vanilla, chocolate, and strawberry. And so that is how you define that type, and then you can use it for the rest of your program. And you're forced to use only these values. Those are the only 3 things that could be in the ice cream type. It's the only 3 valid values of ice cream. Okay? So just like true and false are the only valid values for bool, you can make your own kind of type with other names, okay? Little words inside. So that's enums. We're going to be using those. And then let's remember hash tables, because this lab is on hash tables. So a hash table is just a fancy lookup table. You're using an array or a vector deep down to get somewhere to look up keys. Keys can be things other than numbers. They don't have to be like valid indices. You're kind of using what's called a hash function to like manipulate those down to indices in your array /vector in your lookup table. All right. So hash tables map keys to values. And so this is the C++ standard library version of a hash table. It's an unordered map. You got your key type and your value type. All right. And the idea is that you're going to use the key somehow to get to a value. No matter what the key type is, whatever k is, you need to be able to convert it to a number, because that's going to eventually get you to like a place, an index into an array. You need to convert that key type to a number, and that's called hashing it. Okay? And that number takes you to where in your lookup table you're supposed to place the thing. Or maybe if you're looking it up, like where it was. Okay? It's taking you to where it was. So like maybe, I don't know, you can insert names to phone numbers. That can be your hash table. And if you want to add something, you need to hash my name in order to get to like what index it goes to. And oh no, what if it goes to 2? Like what if the hash function sends it to 2? Okay? And then you place it there. So that's what you do. So, okay. When you have collisions, right? When you have collisions, you have to worry about this kind of stuff. So there's 2 different kinds of hashing, first of all. There's open hashing and closed hashing. And sadly, sadly, closed hashing is called open addressing as well, which is so confusing, disgusting. But open hashing is when like you open up the hash table and you don't store the elements in the table itself. You just use an extra list. So like this is open hashing. It's like if you have collisions like this, Lawton and John Smith are both trying to go to index 2 of the lookup table, then you just kind of let that happen with open hashing. 0, 1, 2, and this is the kind of hash table I made my 41 students implement. You just store a list here, like of all the things that you place here, all the things that went to index 2 that the hash function took to 2, you just put them both there. So you'll store like a linked list of both my name and phone number and John's name and phone number. So there's that. You do have to store, though, no matter what kind of way that you're storing this, you really are secretly storing their name in addition to their number. Like that, you have to store it twice, because like if you just put 2 numbers here, you're not sure like, was this Lawton's number or was this John's number? Because they both went to index 2. So you have to store the keys and the values in the hash table. So that's important. What else? So yeah, open hashing is when you like open up the table for these colliding things. You just like store them outside of this table. You use an extra list or other things. And then closed hashing is when you remain. The table is closed off. You remain within the table. Yeah, you have to store the elements in the hash table itself. So if your hash function took you to 2 and 2 was full, you got to find a different index, something other than 2 now. Okay? And this is the kind of hashing we're going to implement for this lab, because it's more mathematical. It's more in the spirit of this class. This is not the common kind of doing it, though. Most people do open hashing. That's the more efficient way. But who cares? We're going to do it this way for this lab. So what you do for closed hashing is if the spot you're looking for, you're trying to insert like at index 2, and you see that it's occupied, you're going to go and you're going to search for an empty spot somewhere else in the table. Like maybe you'll go to 3 or 13 or something. You're going to search for an empty spot somewhere else, not index 2 now. Index 2 is in use. And so that the process of searching for an empty slot is called a probing strategy. And then there's a bunch of different kinds of that. And so let me teach you each different kind. And we're going to pick a certain kind today to implement in our lab. So probably the easiest probing strategy is called linear probing. All right. First of all, you must save the key and the value in the table. Hopefully it's going to make sense as to why. With enough examples, but you have to save the key and the value, because when you go somewhere, you're like, was this the key that I'm looking for? Can I stop here? Can I stop here? Was this what I was looking for? Okay, so for my example, my running example, let's pretend that we're not doing a normal phone book. Let's pretend that we're doing a reverse phone book. So we have numbers and we're taking them to names. That's easier for me to show, because I don't have to talk about a hash function. The hash function is just like use the numbers themselves. Reverse phone book. And so we've got like, I don't know, we've got a hash table, we've got a table. It's just it's an array or a vector, and it's got indices. Let's say it's very small. It has 3 indices, 0, 1, and 2. And somebody inserted already, or somebody inserts, let's say, the number 55. All right, so let's say that somebody wants to add my name or my number to my name, and so they're going to try and map my number. Let's pretend that my number is just 55 or something, and they want to store that, want to store my name associated with this key. Okay, the key is a number. So we're going to hash the number. What we're going to do is we're going to shrink down the number to something within the table or do some fancy math. And so the hash function on the phone number 55, pretend that that's a real phone number. Let's pretend that the hash function gives me back 0. All right. And so what you do is you look at that table, at that index that the hash function gave you back. You're like, is that empty? If so, you can just go straight there. It's like, all right, I'm going to insert the key 55 mapping to the value Lawton in the hash table. So if there's an empty slot where the hash function takes you, you just fill it in. But otherwise, let's say that I get my cat a phone, and he gets phone number 56. And I want to insert his number and name into my phone book. I'll hash the number 56, and let's say the hash function also gives me 0. It's a very bad hash function. And so we go there, and it collides. And so now we need to pick a probing strategy. All right, we're using closed hashing, so we can't just like make a list here. We have to pick another open index somewhere else. All right, so let's say I want to add my cat's phone number. So the easiest way to do probing is called linear probing. What you do is just like, all right, the hash function took me index 0. If that's full, let's try index 1 next. If that's full, let's try index 2 next. And we'll just wrap around if necessary. So this is linear probing. If we spell that out using math, again, pretend that h is your hash function, then like your iteration, the number, the time that you're looking into stuff, you call that I. Like your first trial is I equals 0. Your second trial is I equals 1. So like there's an I involved. So the next index to try is always the hash function on your key plus your I plus like your current trial number mod n so that you wrap around the table. So like the very first time like you're about to insert something, you set I to 0, of course. Like that's your first trial, your 0th trial. And so you really are just going to the hash function of the key, like seeing if that's open or not. Going to index 0, seeing if that's open. If it is not, then you set I to 1. You're like, all right, I'm going to try I equals 1. And I will like, all right, the next place I'm going to look is the hash of the keys, like 0 plus 1 now. So that takes you to the next index. See how that's going to take you from 0 to 1? And if it'll also take you from, it'll take you from 2 back to 0. It'll wrap around if you get too big. That's what the mod n is doing. So that's the idea. Like this is your trial number, starts at 0, and this is like the mathematical formula that tells you where to look next. But it's really just try the next one, and wrap around. Okay, so that's that. And so under linear probing, my cat's phone number would go to not index 0, that one's full. You'll look at I equals 1, add 1 to your previous hash value, and that takes you to index 1. 56 and Lonzo. So that's how that would work. Okay, I hope that makes a little bit of sense. So that's linear probing. Hopefully you've also seen this in CSCI 41 already, just not implemented it maybe. So okay, so that's linear probing. And what you do is like no matter what kind of probing strategy you have, like this is the easiest one, but no matter your probing strategy, you're just going to stop looking once you find an empty slot. Like the whole point of the probing strategy is to like get you to an empty slot as fast as humanly possible. All right. Here's another one. Here's a more fancy one, because I think you can imagine like if you have a bad hash function, like it's going to take you progressively longer and longer to find a new one. If you like have a bunch of clumps of things, like you're always going to be like next one, next one, next one, next one. Okay, next one, next one, next one, next one. A bunch more times to find an empty slot, and so that's no fun. It's better to jump around the table to find empty slots, and quadratic probing is a different kind of probing that jumps around a bit faster. All right, because with linear probing, you have the problem of clumping. Like just imagine your hash function always sends you to 0. Like it's so hard, it takes so long to find an empty slot if everybody's going to 0. Like you gotta look at that one, and that one, and that one, and that one, and that one. Oh, finally it's open. You just gotta do that all day long. So instead of that, it's better to jump around the table. Like if this one's full, like jump to here, try this one. This one's full, like jump to here. This one's full, maybe jump to here. Like keep on jumping around. That's what quadratic probing does. It's one way of jumping around a little bit better than linear probing. So what you do is you pick two constants, constant 1 and constant 2, and you use those in your probing strategy. You're going to make a quadratic formula where like I is your trial number again. This involves I and I squared. So you take like originally your hash, you try hash because I is 0 and this goes to 0. That's the index that you try. But then after that, you try hash of your key times constant 1 times 1 plus constant 2 times 1 squared. If that's still full, you try your original hash plus constant 1 times 2 plus constant 2 times 2 squared. You see how that's going to start like moving around pretty far and eventually like wrapping around in a weird way? that's what quadratic probing is about. You got to pick two constants, so that's a better thing than linear probing. It's in general, it finds an open slot faster, but the creme de la creme of hashing is closed hashing. It's the king. It's the best one. It's called double hashing. Okay. So here it is. This is the best probing strategy for closed hashing. It's called double hashing. It's when you have a second hash function. You use two hash functions to jump around your table in a much faster way. Okay? So here's the idea. H1 is like your original hash function. Just keep it the same. And like just pretend like, okay, that's like, if it's on numbers, your hash function on numbers can just be like, shrink it down to the size of the table. That's fine. And then H2 can be a second hash function. You need a second one. It can't be the same as your first one. Just can like take integers to the same number or something. Here's an example hash function, a second kind of hash function on integers. You take a prime number, where p is a prime number less than n. You take it and you subtract that. You subtract key mod p from p. That's a second hash function, taking your integer to a different place. Okay. And so once you have two hash functions, here's the next index that you try, where it starts at 0. It's always hash1 of your key plus I times hash2 of your key. So it's going to force you to move around in different weird ways. Okay? So that's the idea. So here's your table. Here's how double hashing works. All right. So indices 0, 1, and 2. So let's say like I want to insert my own phone number first. So hash1 of 55, that's my phone number, takes me to 0. And so when I is 0, you don't use the hash2 at all. It's like, all right, if it's empty, store 55, your name there, it's totally fine and happy. Otherwise, then you start having to increment I. So let's say that I want to insert my cat's phone number. So I'll do hash1 on 56. My cat's phone number, of course. Takes me to 0 again. That's just my original hash value, sadly. And then if that doesn't work, if that's full, hash1 of key, so you're going to set I to 1 this time, then you're going to run your second hash function on the 56. And so let's say that gives back like 2 or something. Let's pretend. And so what you're going to do when I is 1, the next index for you to try is hash1 of key, which is always 0, plus I, which is 1 now, times hash2 of key, which is 2. All that mod n, that will take me to index 2 next. So it's going to jump around the table, 56, Lonzo. And so that's how you put stuff in, and also how you search for stuff. Okay? And actually, thanks to the magic of prime numbers, this strategy is always going to cover every index of the table, as long as you use the second hash function that has a prime number involved. Thanks to the magic of prime numbers, and hopefully your table size should also be a prime number. Thanks to the magic of primes, this will guaranteed going to visit every index of your table in a different order for every key. So quadratic probing, it hops around in the same way for starting values because you only have one hash function. But think of this one. It hops around in a different, weirder way because the hash2 on the other key is different than the hash2 on the first key. Like the hash2 of like 55 was probably like something different. It was probably like 1 or something. Who knows? So that's going to have you hop around differently depending on your key, and that's a very strong kind of difference. Okay? So hopefully that makes a little bit of sense, but this is the kind of probing strategy that we're going to implement. We're going to have two hash functions, and we're going to use double hashing for our closed hashing implementation. Okay. So I think that's all that I wanted to say there. And so yeah, that's how you insert something. You go look for an empty spot, and it's also how you look for something. Because again, you're going to use the hash function. Like I'm going to look up index 50 or key 56. It will start me off at index 0. Like, oh no, that's 55. That's not what I'm looking for. So I'll run this all over again and be like, oh, okay, there's 56. I found it, and I'll give back Lonzo. So that's also how you look up, in addition to insert. Let's also talk about removal, because removal from a hash function is kind of horrible when you deal with closed hashing. It ruins everything. It will be easy to implement, but it's just kind of disgusting to discuss. Okay. So when you remove something, you have to mark that it wasn't, or that it used to be there, that something used to be there. Let me show you why. So here's your table. And let's say that you have, for some weird reason, you've got a table with four rows, 0, 1, 2, 3. And let's say that you inserted a few things. You had like 5 mapping to, I don't know, somebody's phone number, I don't know, person A's phone number. And then you had index 1, or then you had 6 mapping somebody's phone number as well. It's like, this maps to my phone number or something. And then you inserted 7, and like this maps to my cat's phone number or my mom's phone number, something like that. So let's say you wanted to do all that. And then let's say that you wanted to insert stuff, or you wanted to search for stuff. Let's say that you remove the 5. Okay, this ruins everything. Let's say that you remove the 5. Boop. Of course, it's not going to erase everything. PowerPoint is so unkind sometimes. There we go. Let's say that you remove the 5, so like it's empty space. But person A, so it's not really there anymore. It's like ether. It's marked as it's been removed. And then let's say that you are looking for number 6. All right, you're trying to look up 6, and you're using your hash function like hash of 6, and it takes you to 0 first. All right, let's say that there was a collision, and that's why you put it at index 1. Notice how, if you go to index 0 and you find nothing, now that you've removed something, you think that the 6 was never inserted. You think like this key was never put in the table, because like if there's empty space, that's where you would have inserted the 6. Do you see that? When you remove something, you're kind of removing the idea that something used to be there. And so like stuff that was placed in a different spot because something used to be there, you need to remember that. All right. So when you remove something, you have to mark that that index was filled once. All right. After seeing it. So because like you always would normally, you'd stop searching when you see an empty spot, because you'd be like, all right, if the thing that I'm looking for was there, was actually put in the table, it would have been placed at this empty spot, so I can stop looking now. All right. So that informs us that we need 2 different kinds of emptiness. We're going to make an enum called status, and we're going to tag every entry in our hash table with a different kind of status. We're going to have 2 kinds of emptiness. Empty since the start, since we made this hash table. Empty since we removed something, we'll call that empty after removal. And then filled, it has something in it right now. All right, so these 2 are going to be tagged as filled. This one's going to be tagged after we remove as empty after removal, or ER, I guess. And then this is a different kind of emptiness. This is empty since the start. So if your hash function ever takes you here and you're looking something up, then it really wasn't there, because it would have been placed there. Okay, so that's what we need. And this, now that we see empty after removal, we'll correctly go and we'll be like, okay, that means it must be somewhere else. Let me keep on searching. And then you'll eventually find the key that you're looking for. Okay, so you need to mark your hash table with a status flag for each index. Okay, so that's one new thing to store. Okay, that's just to appease removal and make things work better. So that's that one. And so now let's talk about insertion. When you insert in a hash table, this is pretty easy, right? You just hop around your hash table using your probing strategy until you find an empty slot. Let's say that like you've got 2 things filled, you've got an empty after removal here, and you've got an empty since start here. What you do is you just keep on going until you find an empty slot. Either kind of empty is fine. Like, okay, hash function took you here. You just use your probing strategy to find emptiness. Like, okay, this is empty. It's been empty after removal. Or, okay, this is empty. It's been empty since the start. So eventually, you're going to find one of these, and then you'll just replace it and then mark it as filled. Okay, either kind of emptiness is fine for insertion, because you're trying to find something that's empty to make it not empty anymore. So that's insertion. And just be like, all right, I'll put my thing there and fill it in. Now it's filled. Okay, that's the idea. So that's insertion. Removal is kind of what we talked about. Is what you do is you search for the thing you're trying to remove. So you got your big long hash table. you've got your stuff that you're trying to remove. You're like, okay, key 42, I hate that now. I want to get rid of it. So all you need to do to remove it, there's no need to like delete the key and the value. You just mark it as, instead of filled, you change it to empty after removal. You don't even need to replace the stuff there. You can let future insertions replace it. Just need to mark it as empty, and then you'll treat it as emptiness. That's kind of nice. So it's very easy to remove stuff now. We just had to spend some time understanding why we needed this tagging system, okay? The status system. But yeah, to remove something, it's very simple now. Just got to remember it when we're searching. So search and lookup is now the harder thing, okay? Removal, it's removal's fault that this is harder, but here's what you got to do when you're searching for stuff. What you do is you hop around your table. Let's say this is what our table looks like. It's got a couple filled things, 42 key L value, 55 key M value, something like that. And then you have like an empty after removal and an empty since the start. So, okay, according to your probing strategy, and we're going to use double hashing eventually, but that's beside the point right now. What you do is you hop around. If you're searching for something, you hop around until, like, let's say we're looking for, I don't know, my dad's phone number, and like we start here. Like it wasn't placed there, it collided. And so we hop around to here. That was empty after removal. Okay, that means something used to be there. I don't know if that was the thing I'm looking for, if it got removed, or if it was like, if that was colliding with my thing again and it got added into another place. And so I want to keep on searching. So you hop around until you find either a filled element with the correct key or empty since start. Like if you go, pretending we're using linear probing, if you go to empty since start, that means the thing wasn't there because it would have been placed right there if it was anywhere, right? So dad's phone number is not here, sadly. Something like that. That's what you would conclude. Otherwise, like maybe it takes you, you're looking for M, it starts here, goes here, and then it hops you to here, and you find the 55. It really does work out. Okay, so either you hop around until you find either a filled element with the correct key and you give back the value, of course, because you're trying to look it up, or if you find an empty since start element, that means the thing that you were looking for would have been inserted there if it was there at all. So you didn't find it and indicate, like throw an exception or something like that, saying that you didn't find it. All right, so you keep looking when you see empty after removal. You keep looking when you see something filled with a different key, because that was not what you were looking for, because they were colliding, you imagine. And then also, one last special case is if your entire hash table is filled or has empty after removal, there's no empty since starts, you stop looking once you visited n nodes in your hash table. The probing strategy for double hashing is guaranteed to take you through the entire n nodes in some order. If you've visited all n, you don't want to stay in a while loop forever and ever and ever, because you're never going to find it. Once you've seen all n nodes, you got to keep track of that and be like, okay, I'm done now. I didn't find the thing. Okay, so that is closed hashing in a nutshell and probing stuff. So let's go over the write-up. These are the kind of operations you'll be implementing. Let's go over the write-up and look at the code. That's here. So, okay, this is all about double hashing. Here are the files that you have. The type is called a hash map. And so you're going to be implementing the hash map class. All right. Not a lot of instructions here. It's the slides really are telling you what you need to do. Go back to your CSCI 41 textbook, probably will be extra helpful. But hashmap.h is where the hash map is defined. Oops. Well, that's where I'm defining stuff. I've got my status. I've got my hash table items. So and then here's my hash map class. This is a hash table. This is your hash table. So you're making an object of type hash map, and it has a constructor. It has an insert for keys and values. We're pretending that we have int keys and string values, just like what I've been drawing, just to make it easy on us, to make easier double hash functions. We have an exists method to check if a key exists in the hash table, has a value associated with it. We have a .at, right, just like for normal maps and unordered maps in the library, in the standard library, to go to a key and get back the value as a reference so that we can maybe change it. And then we have a removal method, okay, that gets rid of a key, does not associate it with a value anymore if it's already in there. So, okay, Then we have a bunch of private helper methods that look for stuff. Check if a number is prime. Here are 2 hash functions. Here's one that finds an empty index based on a key. Here's one that finds an index of a key given a key. See if it's there or not. So these will help you implement these other ones. And then here are the pieces of data that are part of our hash table. We have a vector of hash table items. That's our hash table. So the vector of hash table items, every hash table item, every element of your hash table, right? It's got to hold a key and a value and a status. So here we go. Key, int keys, string values, and a status that is by default empty since the start. Okay? That's what hash table items are all about. And then we also have, we're going to have to find a prime number to make our second hash function. So p, we're going to find a prime number smaller than our table size. It's used for our hash2 function. So you'll generate that in like the constructor. Okay, so that's hashmap.h. You'll be implementing most of those methods in hashmap.cpp for our hash table ints are keys and strings are values. Hopefully you still have your CSCI 41 textbook, or you saved it as a PDF if it was a virtual one. That's pretty much all you need. Just look at the pseudocode there. If you don't have your textbook anymore, you can use this link. This is my best link that I could find about double hashing, but that's the key term that you're searching for here. You're searching for double hashing. That's the kind of pseudocode you're looking for. That's the thing that you're implementing here. It's not going to be the same as all this, but it's going to be very similar, and it's going to write about what's going on. Okay, so that's that. It doesn't talk about remove, though. Just follow my slides. For removal, just legitimately mark it as a different status than you have removed it. Let's see what else. I've tried to be helpful with my comments. So here's the comments. Here's the CPP file where you're going to be implementing stuff. Oops. So here's the constructor, for example, of hash maps. You're going to, I set the size of the table this way. This makes a table of that exact size. And then I want you to also set the p member variable to be the first prime number smaller than size, because that's going to help for the hash function, okay? Because this is our second hash function. It needs a prime number to work properly. And so you can use your lab00 implementation for this. So you just need an inst prime helper function. That'll help you search for the first prime p smaller than size. So you just have a loop here that uses this. So that's that. I've given you the 2 hash functions that were needed, that we're going to use for closed hashing. And then here is you implementing the probing strategy. All right, so here's our first helper method called find empty index. Okay, so I want you to implement this and go to and find an index in the table that is not yet filled. You can assume that there always is one, so you don't have to do any extra checks if you don't want to. But you're going to use double hashing to find an empty index. So it's going to be hash1 of key plus I times hash2 of key mod the table size. That's going to be the next index that you look to as you probe. Okay, so that's double hashing. Where's that? This one. So it's exactly this. That's what you're going to be implementing to find an empty index. All right, so you're going to be looking into the table. So take your key, hash it, start an I, starting at 0, and start looking at these indices until you find one that has been marked as, because it's a hash table, right? Oops. Every hash table item, like your hash table is a bunch of hash table items, go to all these indices and check the status. Is it empty? Is it some kind of emptiness? Is it not filled? Return that index. All right, find the first one that's not filled. Okay, so that's your first helper method. And then this is find index of key. This is going to help you when you look up stuff. This takes a key and it looks for the value, if it's there or not. All right, so this gives you the index in the table that has the key. You're gonna search for it in the way that we were talking about, using your probing strategy. And you're going to give back the index in the table where it was, or -1 if it doesn't exist in the table. This will help you for the lookup function. All right. So again, you're going to use the probing strategy on the key. So you're going to go use your probing strategy, starting with this key, starting I at 0, go until you find either like the key that you're looking for, or something that marks that it wasn't there. So keep looking, keep searching, right? Keep probing if you see empty after removal, and stop if you see an entry that is empty since start, right? If you see something that's filled, you just check the key. Does the key match? Okay, but yeah, just watch out in case the table is full. If there's nothing that's empty since start, It's possible that everything is empty after removal or filled at some point in your hash table's life. And so at that point, you need to stop once you've seen all of the entries in the table. So you've visited that many, right? The size of the table entries. In that case, it wasn't there, you can return -1, because that's what you're supposed to do for this one. And then insertion in the hash table is, again, like go there, insert key mapping to a value. If the key's already there, like you can maybe try this, see if it's there or not. If the key's already there, update its value. Otherwise, you're going to have to find an empty index using your other helper function to put in the key and the value. Okay, so you'll set the key and the value in the slot, and remember to set the status to filled so that you don't like overwrite it and think it's empty in a weird way. Okay, that's important. This is to check if the key is somewhere in the hash table, so you can, of course, use one of your helper functions for that. And then here's your .at. Okay, this should not compile right now, but you're going to give back a reference to the key's value. Okay, so what you do is you return the value that is mapped to by a given key. So you're going to see if it's there in the table, hopefully it is, and then you give back, because every key is associated with a value in its hash table item. So you go to the index where it is in the hash table, where that key is there, you give back the value as a reference. Just return it and it will give it back as a reference. That's fine. If there is no index where that key lives, like you're going to use your helper method, and if it gives it back -1, then just go there. It's fine. Just let table.at throw that exception, because it's the user's fault. They should have checked using exists before using .at. Okay, so just let it fail. Let the exception get thrown. Just pretend that it's going to work. Just use the find index of key and just go to that index. It's fine. Let it throw an exception if the key wasn't there. Right, and then finally remove. That's like all these things are difficult because of remove, but remove itself is pretty easy, right? Just go to the key that you're trying to remove. Don't even have to like replace its values with that key or value with anything weird. Just like set its status to empty after removal. Okay, no need to change the value since as you're searching for stuff, you're skipping anything that's empty, right? Or you're inserting over empty things, so you're good to go. So that's hash map. That's everything. That's what you're implementing. I've given you the hash functions. You just got to use them. Implement double hashing. Okay. So I've made some tests for you in the test hash map file. The make file is going to compile all that fun stuff for you. So you just say make test hash map. Here's the testing file. It's checking all your stuff. It's using randomness. So run your tests a few times maybe, but here's like a simpler test where we're going to make a hash map of size 101, inserting some things, and then checking that all the values are in the right spot, some stuff like that. Ensure that they exist, ensure that their values are correct, then make sure that I can update stuff, make sure that I can remove stuff, etc., etc. Your exist should say that it's not there once it's removed, right? And then here's a more complicated one. This involves just a bunch of numbers. Here I am filling up the hash table with some values and some strings, making sure they're all there. I'm deleting some of them. I'm overwriting some of them, and making sure that they got overwritten. So just follow along. Use GDB for sure if things start going weird. Checking for stuff. Just follow. This is just a more complicated test, making sure that things are getting deleted, etc., etc. So those are my tests. Definitely make sure the first one's the simpler one to understand. So get that passing first before you try to tackle the second one. Hopefully, if the first one passes, so should the second, in theory. Though it is a bit more complicated. So get those to pass, and that's what I'm grading you on. So that's everything. You'll turn in the one file that you change, which is hashmap.cpp, and that's pretty much it. So yeah, that's your lab 3. It's on hash tables and double hashing using the magic of essentially modular arithmetic all over again, just like for encryption, to do some cool stuff. So yeah, that's your lab 3. Please yell at me if you have any questions, and good luck.